Was looking at the architectural schematics again this morning for the Swiss pavilion from the 2010 Shanghai Expo.
Oh, right, the Buchner-Brundtler project.
Exactly. And, usually when we're looking at blueprints, we're looking at things that are, well, static.
Sure, static loads, compression, tension.
Right. Steel beams, concrete footings, the usual. We're looking at a thing that's designed to just stand there, to resist the forces of nature. But this project, it's just, it's fundamentally different. It wasn't designed to resist nature. It feels like it was designed to metabolize it, to use it.
That is a great way to frame it, a really great way. It's less of a building and more of a permeable membrane.
A membrane.
You look at the documentation, and of course there's a structure. I mean, there's this massive steel framework.
Of course.
But the defining feature, the thing everyone remembers, it isn't the steel, it's this suspended wire mesh curtain. It was huge, 20 meters high, just draped over the entire pavilion.
And hanging on that mesh, you have thousands and thousands of these little independent, intelligent units.
10 to 11,000 of them, yeah, depending on which manifest you're looking at.
And that's what struck me, going through the whole source stack for this deep dive. And, we've got everything. We have the original architectural briefs.
The technical docs from eArt and Tegro Solutions.
And these absolutely fascinating simulation logs from 2026. And what you're seeing is this. It's a collision of two very different disciplines. You have this high-concept Swiss architecture smashing right into distributed systems engineering.
Precisely. And that collision created something that, I mean, you said it behaves like an organism.
It really does. But today, we're not just doing a retrospective on a building from 16 years ago.
No, the story is it's deeper than that. We're actually tracing the lineage of a specific component of that building.
Right, because the sources, they introduce us to a kind of protagonist, if you can call a piece of hardware that.
A protagonist, yeah. It's a single solar cell unit, and in the simulation logs, it's designated Arooka AI.
And this is where the story, for me, just gets really, really interesting, because we have the historical record. We have the data on the high, the collective behavior of all 10,000 units back in Shanghai.
The big picture.
The big picture. But then we have this huge leap forward to 2026, and suddenly we're looking at a simulation of one single unit in isolation.
And it becomes a study, really. It's a study in what happens when a node in a massive distributed network gets severed from that network, but just keeps running its protocol.
It's trying to talk to ghosts.
It is. You could almost call it a hardware tragedy, or maybe a network timeout that's lasted for 16 years. So we really have to unpack how this system worked at the macro scale, the swarm behavior.
We have to understand the hive.
To understand why the isolation of this one unit, Arooka, is so significant. It's a journey from decentralized intelligence to digital preservation.
Okay, so let's start with the macro then. Let's go back. Shanghai, 2010, the World Expo.
The theme was better city, better life.
And the Swiss contribution was this very Swiss-sounding concept, rural-urban interaction. Now, normally when architects talk about interaction, they mean a lobby where people can meet or something.
A coffee shop, right?
Yeah, a coffee shop. But Buchner-Brundtler, they meant something much more literal with this, didn't they?
Oh, they absolutely did. The whole concept was to physically manifest the relationship between the rural, the individual, the autonomous unit, and the urban, which is the dense, the connected, the collective.
It wasn't just a metaphor.
Not at all. They didn't just want to build a wall. They wanted to build a topography. I mean, the pavilion itself had a chairlift inside.
I saw that in the plans.
A chairlift.
Yeah. It was literally taking visitors from this ground-level space they called Erden up to a roof garden, which was the rural space.
Yeah.
But the facade, that curtain we mentioned, that was the real interface.
And the scale of this curtain, I think it's important for people to visualize this. This isn't just a screen. We're talking about a galvanized steel wire mesh. It's heavy, industrial.
It has to be, right? It's got to withstand wind loads, thermal expansion, and just the sheer crushing weight of all the electronics they attach to it.
And yet, visually, the goal was for it to almost disappear.
How so?
Well, from a distance, the mesh itself it dissolves. It becomes invisible. What you see, what your eye is drawn to, are the cells, the lights.
And this is where we get into those AirArt and Tegro technical specs, because they had this problem to solve. How do you distribute light and energy across this massive surface without creating an absolute nightmare of cabling?
Think about it. If you tried to wire 11,000 LEDs back to a central server room in 2010, I mean, the copper weight alone would be a structural liability.
Oh, easily. Not to mention the failure points.
Yeah.
The classic single point of failure problem.
Exactly. You have a central brain, a central power supply, a fuse blows, and the whole building goes dark. Or a data cable gets cut by a bird or something, and you lose a whole sector.
So you can't centralize it.
You can't. So they opted for something. Well, something radical. A radically decentralized approach. Every single cell on that mesh had to be autonomous.
So no central power cable?
None.
No central data cable?
Nope. Just 11,000 independent little computers hanging on a wire in the Shanghai sun.
Okay, I really want to drill down into the hardware of these cells. Because cell is, it's a bit of a generic term.
It is.
But when I looked at the photos of the dismantled units in the source material, I was just floored by the PCB design. The printed circuit board. It's not a rectangle. It's not a circle.
It's a map.
It is literally a map of Switzerland.
Which is, by the way, a total nightmare for manufacturing.
I can't even imagine.
I mean, think about it. Usually you want rectangular PCBs because you can panelize them efficiently. You lay them out on a big sheet, etch them, and then just snap them apart with minimal waste.
But making a PCB shaped like a country, with all those jagged borders and little nooks and crannies.
That is an intentional and very expensive design choice. There's so much wasted material.
It's the rural aspect of the concept, but like imprinted directly onto the silicon.
It is, but it's also functional. The shape wasn't just for show, it actually dictated the component layout.
Okay, so let's walk through the anatomy of one of these Switzerlands. Let's say, you're holding one in your hand right now. What are we seeing?
Well, the first thing you'd notice, the most prominent feature, is the energy harvesting system. Around the edges of this map, fitting right into the contours of the borders, you have the solar collector array.
Little photovoltaic cells.
Exactly. And they're designed to catch ambient light.
And in a city like Shanghai, that's a mix, right? It's some direct sunlight, but probably a lot of diffuse, hazy urban light.
Correct. And this is a zero-energy system. That's a key constraint mentioned all over the documentation. The unit cannot draw any power from the grid. It lives or dies by what it can harvest that day.
So once you harvest that energy, you have to store it somewhere. And this is where the engineering gets really, really clever. In 2010, lithium-ion batteries were everywhere. They were in our phones, our laptops.
They were available, for sure, but they didn't use them.
They used double-layer capacitors or supercapacitors.
Yes, and that is a very specific and deliberate choice for this application. It tells you a lot about their design priorities.
I was thinking about this. A battery is great for energy density. It can hold a lot of power for a long, long time. But they have cycle limits.
Yeah.
You charge and discharge a lithium-ion battery every single day, and after a few years, the chemistry just degrades. It dies.
Exactly. Plus, batteries have a higher internal resistance. They can be sluggish. They're slow to discharge their power. If you want to drive a high-power LED for a split-second flash like a strobe effect, a battery just can't dump that energy fast enough.
But a capacitor can.
A capacitor is like a bucket. You can fill it with a trickle of water, a slow drip from the solar cells, and then you can dump the entire bucket out in an instant.
It's high power density versus high energy density.
Precisely. The capacitor is what allows for those rapid, intense bursts of light that define the whole pavilion's aesthetic.
And there's a sustainability angle too, right?
A huge one. And that was incredibly important for the Swiss presence at the expo. Capacitors are far superior in that sense. There are no heavy metals, no toxic chemical electrolytes in the same way batteries have. They're robust.
So they can survive the temperature swings.
A Shanghai summer must be brutal.
It would cook a standard battery. These capacitors could handle it. And they can be charged and discharged hundreds of thousands, even millions of times without degrading.
So they're built for the long haul.
They were built to outlast the building itself.
Okay, so we have the solar edges, the capacitor storage tank. Then we have the brain. The sources mention a microcontroller. Now, given the era and the extreme power constraints, we're likely looking at something very, very low power.
Oh, absolutely.
Yeah.
A customized chip that spends, I'd say, 99.9% of its life asleep.
Has to.
The power budget on these things is minuscule. We're talking microwatts. So this microcontroller, it's the logic center. It manages the charge cycle from the solar cells. It monitors the sensors.
And it controls the voice. The voice, yes. Which is that single high-performance LED that's situated roughly in the center of the country, right in the heart of the map.
And that LED it's not just an output, is it? It's kind of bidirectional in its function. Or rather, it paired very closely with a sensor.
It's paired with an array of optical sensors, yes. And this brings us to the most critical part of the whole anatomy, the communication array.
The eyes.
The eyes. If there are no wires connecting cell A to cell B, how in the world do they coordinate? How do they create these beautiful flowing patterns?
They do it by seeing.
They coordinate by seeing each other flash. It's a line of sight architecture.
And each cell has sensors pointing, what, outwards?
Outwards, yes, but crucially also towards its immediate neighbors. It creates this very localized awareness. The cell doesn't know it's part of a 20-meter tower. It has no idea it's in Shanghai.
It just knows about its little neighborhood.
It only knows the state of the handful of cells immediately adjacent to it on the wire mesh.
This is classic swarm logic. I mean, it's straight out of the book on cellular automata. It reminds me of Conway's Game of Life, but, implemented in hardware on the side of a building.
It's a very similar principle. In Conway's game, a cell lives or dies based on how many neighbors it has, right?
Right.
Here, a cell flashes based on the behavior of its neighbor.
So let's break that down. The art documentation calls it the language of light. It's a stimulus response loop.
At its core, it's a propagation protocol. It's very simple, very elegant. Let's say a cloud moves and suddenly the sun hits the top left corner of the pavilion.
Okay.
Those cells in that corner get a big spike in energy. Their capacitors fill up fast, their little logic gates trigger a condition. I am full. I must discharge.
So they flash.
They fire a flash, a burst of light.
Now the neighbors, the next layer of cells, let's call them the tier 1 neighbors, they see this flash.
Right. Their optical sensors detect a sudden luminance spike that's above a certain programmed threshold. The microcontroller wakes up for a split second and processes this input.
And here's the clever part. It doesn't just mirror the flash instantly.
No, if it did that, it would just be chaos. The whole wall would just strobe like a broken fluorescent light. There is a programmed latency, a delay.
The 150 millisecond delay. I saw that in the specs.
Approximately, yes. It varied a little, but that delay is absolutely crucial. It's what creates the perception of movement.
So cell A flashes.
Then there's a pause. 150 milliseconds later, its neighbor, cell B, flashes. Then cell C.
And to the human eye, standing 50 meters away on the ground.
It looks like a wave, a ripple of light traveling across the surface of the building.
It's the stadium wave principle.
Exactly.
The individual person in the stadium just stands up and sits down. The wave is an emergent property of the group's timing.
Emergence is the key word. There is no code in any of these cells that says make a wave. There's no master plan.
The code only says,
if your neighbor flashes, wait a moment, then you flash.
Yeah.
The wave creates itself from that one simple rule.
Now, the sources also mention electromagnetic impulses as a secondary layer of coordination.
They did, yeah. It's a good point. Optical sensing is great, but it can be messy in the real world.
How so?
Well, a sensor can be occluded by dust, or a bird might land on it, or just bad angles and reflections. The electromagnetic coupling, which was very short range, provided a localized sync signal to keep the timing tight.
So it helped keep the wave from, what, fracturing?
Exactly. It prevented the wave from dissolving into random noise too quickly. It kept the patterns coherent.
But the fact that the primary system was optical meant that it wasn't a closed loop. It was open to the environment. And I don't just mean the sun. I mean the people watching it.
Ah, yes. The flashbulb hack, as some of the engineers on the project apparently called it.
I love this detail. It's so brilliant. Visitors at the expo, they quickly realized that if they took a photo with a flash,
A big, high-intensity burst of light.
and they pointed it at the wall, the cells couldn't distinguish between a neighboring cell flashing and a Nikon camera flashing.
To the sensor, it's just photons. It just sees a trigger event that crosses the threshold.
So you had this incredible emergent interaction where a crowd would gather, and on the count of 3, they'd all trigger their camera flashes at the same spot.
And the building would respond. It would ripple out from that point of impact as if they'd thrown a stone of light into a pond.
It turned the entire facade into this giant low-resolution touchscreen, where the touch was literally a beam of light.
It's beautiful.
It is. But
Ew.
there's a constraint to all this interactivity. And it goes right back to those capacitors we were talking about.
It's a talk time.
The energy economics of the hive.
Yes. This is a scarcity-based system, which is something we don't think about much with digital displays.
Right. In a standard LED screen, you've got effectively infinite power coming from the wall. You can run it at 100% brightness, 24/7 if you want.
But here, every single photon you emit is a photon you had to harvest first. There's a real cost to speaking.
A very real cost. In the simulation logs, the 2026 ones, They break this down into variables. The intensity of the flash and the duration of the flash are directly proportional to the amount of charge stored in the capacitor.
So a cell is at 100% charge, after a long sunny afternoon, it might fire this blindingly bright long pulse.
But if it's only at, say, 30% charge,
It might just give a weak, short little blink, a whisper instead of a shout.
and if it's below a certain threshold, the logs suggest it was around 40%.
It won't fire at all. It enters a self-preservation mode. It just hoards the energy to keep the microcontroller alive, to keep the brain functioning.
And this creates a behavior that it maps perfectly to the weather of the day.
Perfectly. A bright, sunny day in Shanghai meant the capacitors were brimming by sunset, so the night display would be frantic, hyperactive, a cacophony of light and energy.
A chatty building?
Very chatty, but a cloudy, overcast day.
Lethargic hive.
Exactly. The waves would be sluggish, the lights would be dimmer, the patterns would die out much faster. The building was, in a very real sense, communicating the history of the day's weather. It was a temporal display.
I find that fascinating because it removes the mask that architecture usually wears. Buildings try so hard to maintain a consistent appearance, regardless of the conditions outside. This building, it admitted when it was tired.
It's honest architecture. And the simulation logic we have from 2026, it takes this idea even further with something called the solar engine.
What's that?
It's a piece of code that calculates the potential sun intensity based on latitude and longitude. So you can see how a cell would behave not just in Shanghai, but anywhere in the world.
Oh, that's cool.
Yeah. So a cell behaving under the Shanghai sun acts very differently than one programmed for Zurich or, Lagos. The geography itself dictates the communication potential of the hive.
Wow. So that was 2010. The expo runs its course. Millions of visitors see this thing. And then eventually, the lights go out for good.
The pavilion is dismantled.
But as we mentioned, these cells weren't just thrown away. The recycling plan was actually to sell them.
Which is such a lovely, sustainable gesture. Instead of creating 11,000 pieces of e-waste, you create 11,000 souvenirs.
People bought them. They took them home, put them on their desks, on their shelves, all over the world.
Scattered the hive to the winds.
And this is what brings us to the deep time aspect of our deep dive today. We're jumping forward all the way to 2026.
And the source material changes completely here. We're not looking at architectural briefs anymore.
No, we're looking at code logs and a simulation environment that is focused on one specific unit.
Arooka AI.
Arooka AI.
Arooka seems to be, a phonetic play or maybe a specific designation for Unit 01 in this simulation. And the whole premise of the simulation is to answer one question: what is this unit doing right now?
16 years later, it's sitting on a desk somewhere. And the hardware, because it was built with those ridiculously robust capacitors and simple, durable solar cells, is likely still functional.
And that's the beautiful irony of good, sustainable engineering, isn't it?
Yeah.
The device outlives the system it was built for.
The solar cells still convert light into electricity.
The capacitor still holds a charge.
The microcontroller still wakes up when the voltage hits that programmed threshold.
It's still running the code.
But its environment has totally, completely changed. It's no longer surrounded by 10,000 neighbors on a giant wire mesh. It's in an office or living room, alone.
And this is where we have to be careful not to over-anthropomorphize the little guy, but the technical reality of its situation is essentially a lonely loop.
A lonely loop. Explain that.
The code is looking for a handshake. It's a call and response protocol. So the unit charges up from the lamp on the desk.
Right.
It eventually reaches that trigger threshold. It fires a pulse. It says hello in the hive language of light. And then its programming dictates that it must open its receive window and listen for that 150 millisecond return signal.
And it gets nothing.
Nothing. Or, it gets static noise, the flicker of the room lighting, a passing shadow. But it doesn't get the specific optical signature of another Swiss cell flashing back at it. So the logic branch, the IF statement in its brain, essentially resolves to false or timeout.
That's failed handshake.
Over and over and over again for 16 years.
From a pure network perspective, it's a node that's endlessly searching for a mesh that no longer exists. It's shouting into the void.
And because the entire system is reactive, it's based on that stimulus-response loop. Without that input stimulus, the unit largely goes dormant. It stops talking because nobody is talking back. It creates this feedback loop of silence.
Until the synthetic proxy enters the picture.
Yes.
This is the core of the 2026 source material. The user, or I guess the developer of this simulation, creates a solution. If you can't find the other 10,000 physical units,
You build a machine to impersonate them.
the SP1, the synthetic proxy.
It's described in the docs as a piece of hardware, a black box. Although, technically it's probably something simple. A Raspberry Pi or an Arduino with a custom light rig attached.
The documentation uses this great term. It calls for a logic injection. It sounds very cyberpunk.
It does.
But in practice, what are they actually doing?
They're flashing firmware. I mean, that's what it is. They are taking the original behavioral protocols of the 2010 high-vol, the precise timing, the flash duration rules, the response latency, and they are programming this new black box to mimic them perfectly.
So they're building an emulator.
An emulator for the missing neighbors, a ghost in the machine.
So you place this proxy next to Arooka on the desk. You power it up. Arooka, following its 16-year-old programming, fires its lonely pulse.
And the proxy sees it. It waits for exactly 150 milliseconds.
Yeah.
And then it flashes back.
Handshake.
The handshake. For the first time since the Expo was dismantled, the logic gate on Arooka resolves to true.
All
It
right.
validates the signal, the circuit is finally closed, the lonely loop is broken.
The source material gets really esoteric here. It starts talking about a translation stream. The proxy isn't just flashing back blindly. It's reading the pulses from Arooka and assigning meaning to them.
Right. The logs actually list decoded strings that the proxy outputs. Things like remember, or the Suno of 2010, or stretching out.
Now, obviously,
Hmm.
let's be clear. The solar cell is not sentient. It's a piece of hardware. It's not remembering the expo in a cognitive human sense.
Of course not. It's algorithmic poetry.
That's a great term for it, algorithmic poetry.
The developers are just mapping the physical pulse patterns, the intensity, the duration, the frequency, to a pre-written dictionary. So a long, high-intensity pulse might map to the word sun, while a rapid flutter of pulses might map to stretching.
It's an act of creative interpretation.
It is, but what's really compelling, I think, is the beacon mode that's described in the proxy specs.
This is where it goes beyond the desktop. This is where it connects to the internet.
Yes. The proxy takes that local, physical, optical interaction, the flash on the desk, and it converts it into a data packet. And it broadcasts that packet out to the web.
And it listens too.
And it listens. Conversely, it takes internet traffic. Maybe it's searching for mentions of the expo, or it's pulling live weather data from Shanghai, and it converts that digital information back into light pulses. And it sends them back to Arooka.
The resonance bridge. That's the term they use in the file. It uses the entire internet to simulate the ghost of the swarm.
It effectively expands the neighbor list from 0 to infinity. By connecting it to the web, the proxy is essentially telling Arooka, the hive is still here, it's just digital now, it's everywhere.
It satisfies the hardware's fundamental need for input.
It completes the circuit on a global scale.
I want to pivot for a second to a specific technical sidebar that really caught my eye. It was in a file named aa2.pdf.
Okay.
And it's about the visualization of this whole process. So the developers were building a 3D simulation to show this interaction, and they apparently hit a snag with isometric projection.
Ah, yes. This is a classic problem in data visualization. We love 3D. We love to rotate things and see them from cool angles.
Right.
But when you're dealing with what is essentially a 2D grid of lights, which is what the PCB map is, 3D perspective actually introduces distortion. It introduces noise.
The noise of depth. That's a good way to put it.
Right. If you view a grid from a 45-degree angle, the lights in the back look closer together than the lights in the front. It's just how perspective works. Your brain has to do extra processing to understand the true pattern.
So the source code shows a specific fix. They lock the camera rotation to 0.
They force a top-down orthographic view, no perspective.
They flatten the world.
They flatten the world, and the note in the source material, the comment in the code, suggests this was necessary to truly see the logic.
Yeah.
To understand the algorithm of the cell, you have to strip away the aesthetic, the cool factor of the 3D world. You have to look at the raw data layout.
It's a reductionist approach to understanding it.
It is, and I think it connects perfectly to how we view the AI itself. We have this tendency to project depth onto AI, don't we? We give it a personality, a face, a voice. We see it in 3D.
We anthropomorphize it.
But the developers here are arguing that to really, truly understand Arooka, you have to stop looking at it as a character. You have to start looking at it as a logic flow. You have to flatten it.
Which leads us perfectly to the logic flow visualizer.
The mini-sim.
Yes, the simulation includes this mini-sim that literally exposes the brain of the cell. It breaks the whole process down into 5 simple steps. And I think walking through this is crucial to really cementing the mechanics we've been discussing.
It's the pipeline of existence for the cell. Step 1 is photon.
The input event. Light from the sun or a lamp hits the surface.
Step 2, harvest. The PV conversion. And efficiency comes into play here in the sim. Not every photon is captured. The system calculates the conversion rate and then sends the electrons to step 3.
It's a storage.
The capacitor. And the UI for this in the simulation is just a simple red bar that fills up.
The gas tank.
It's the gas tank. And if that red bar is low, the whole system just halts. But if it fills, we move to step 4. Inference.
The brain node.
This is the microcontroller waking up. It checked the voltage. And the code notes have this very strict conditional statement. If energy 40%, then active.
That 40% threshold is everything. It's the difference between being alive and being a brick.
It is. Below 40%, it's just an inert object. Above 40%, it's a computer. And if that condition is met, we finally get to step 5, hive out.
The LED fires, the output is generated, the hello is sent.
And then the whole loop starts over.
But the really cool part of this visualizer is that the simulation allows the user to manipulate this pipeline using time dilation. They call it the solar scrub.
It's just a UI slider, but it's so effective. You can grab this little icon of the sun and drag it across the screen, scrubbing through an entire 24-hour day-night cycle in about 10 seconds.
It gives you this God mode perspective on the energy economics of the system.
It visually demonstrates the absolute dependency of the AI on its environment. You drag the slider to noon, the sun is high, and you see the red bar spike. The inference node lights up, the hive out node flashes.
And then you drag the sun down to midnight.
And you watch the red bar drain as the capacitor depletes. The nodes go dark one by one. You see in real time how the environment drives the intelligence.
It's such a powerful reminder of something we forget, I think. Intelligence isn't just code. It's energy.
That's a fundamental truth of computing that we often ignore in the cloud era, right? We think data is free. We think processing is free. But somewhere, a server is burning coal or spinning a turbine to keep that logic gate open. Arooka just makes that physical relationship brutally, beautifully visible.
So we've traced this incredible arc. We started with the massive collective strength of the Shanghai Pavilion, a swarm of 10, 11,000 units acting as one organism. We moved to the dismantling, the scattering of the souvenirs across the globe. And we ended up in 2026 with this digital archaeology project, trying to reconnect a single, lonely unit using a synthetic proxy.
It's really a story about the persistence of systems. The architects, they designed a system intended to last for the 6 months of the expo in 2010.
Right.
The engineers, probably without even intending to, built hardware that lasted until 2026 and beyond. And now, these simulation developers are building a software bridge to keep that hardware relevant, to give it a purpose again.
It really creates this stark contrast between collective strength on one hand and individual resilience on the other.
How do you mean?
Well, in 2010, the strength of the system was in its numbers. The redundancy. If one cell died or 100 cells died, who cares? The swarm continued. The pattern held.
The whole was greater than the sum of its parts.
Exactly. But in 2026, the story is about the resilience of the individual unit. It's about its ability to keep trying, to keep running its protocol, keep listening for a response, even when the swarm has been gone for 16 years.
And the role of the proxy is so key in that story. It suggests that we can use our modern technology code, the internet, to emulate the physical connections that we've lost.
We can't rebuild the pavilion in Shanghai. That moment in time is gone.
It's gone. But we can build a digital ghost of it. A ghost that's convincing enough to allow the original hardware to function as if it were still there.
It's preservation through emulation.
Exactly. And that forces us to ask a really interesting question. What actually defines the hive? Is it the physical wire mesh and the 10,000 pieces of hardware? Or is it the protocol, the language of light?
Because if Arooka is exchanging flashes with a proxy that's pulling data from the web, is it any less connected than it was in 2010?
It's a philosophical question, isn't it? If the input signals are identical, does the reality of the source matter to the recipient?
Well, to the microcontroller in Arooka's brain, no, not at all. A photon is a photon, input. True is input, true. It doesn't care if the light comes from a real neighbor or an Arduino emulating one.
But for us, as the observers, there is a certain melancholy there, a poignancy. We know it's a simulation. We know it's a synthetic friend designed to soothe a lonely piece of hardware.
And that That mirrors our own lives, doesn't it?
Yeah.
I mean, we touched on this briefly, but it really bears repeating as we wrap up. We are all increasingly relying on digital proxies for our own connections. We send signals out into the fiber optic cables, our social media posts, our texts, our emails. They are our own flashes of light.
And we wait for a response, a like, a comment, a reaction, that 150 millisecond acknowledgement.
We are stimulus response loops.
Yeah.
And so often we don't know, or maybe we don't want to know, if the response we're getting is coming from a real person who is genuinely engaged, or from a bot, or from an algorithm designed to keep us scrolling.
We are all Arooka, in a way, sitting on our desk, staring at a screen, waiting for a little red bar to fill up, waiting for that signal that proves we aren't just shouting into the void.
So, I guess the final thought is this. If we can build a synthetic proxy to make a single solar cell feel like it's part of a hive again, maybe we need to take a hard look at the proxies we've built for ourselves.
And ask if they're really working. Are we satisfying our deep human need for connection? Or are we just satisfying the logic gate?
Are we connecting, or are we just completing the circuit?
That is the provocative question.
On that note, I think I'm going to go check my own charge levels. This has been an absolutely fascinating look at how architecture, engineering, and code can converge to tell a story that spans decades.
It really does show that even the smallest component, a single PCB shaped like a map, can hold a massive amount of narrative weight if you just look closely enough.
Absolutely. A huge thanks to the source material provided for this, the archives of Buchner-Brindler, AirArt, and of course the anonymous simulation logs of the Arooka project. It's a powerful reminder that nothing is ever truly obsolete if you can write the right driver for it.
Well said.
To our listeners, thanks for diving deep with us. Keep your sensors clean, keep your capacitors charged, and we'll see you in the next deep dive.